All right, great. Thank you so much for the invite for the organizers, Q2B Paris, to be here. It's a true honor to talk about the work we're doing at the Air Force Research Laboratory. I'll talk a little bit about what we are and what we do in the next few slides over the course of this presentation. But really wanted to give you a feel for where we're going. I've talked for several years now some of the qubit technologies we've been developing for networking, and now these new results kind of put it all together in terms of an architecture framework. So the U.S. Air Force, AFRL, Air Force Research Laboratory, we are the science and technology arm for the United States Air Force. Air Force includes both Air Force and Space Force. So hence you see some really nice representations here of space work we're doing as well. This is what we call our operational view of where we really see our technology going. So I'll just take a couple minutes here to walk you through it. Four main areas of our quantum strategy: timing, sensing, networking, and computing. When we talk networking, of course, communications goes in there as well. We're going to spend, of course, the bulk of the talk on that. In terms of timing and sensing, so timing, you think of clocks, you can think of long holdover times, stability, size, weight, and power, all things we're driving towards for practical Air Force applications. In terms of sensors, combining those with quantum sensors, in particular, we're interested in accelerometers and magnetometers for gravity map matching as well as magnetic map matching. Why we're interested in those would be operating in GPS denied and contested environments where we need long duration unaided inertial navigation systems. On the networking side, of course, low probability of intercept communication, secure communications, linking together quantum computers, quantum processors, linking together quantum sensors or quantum clocks are really our targets. And we see that as a real rich area for further investigation. I'll spend a couple minutes at the end of the talk, if we have time, to go into our quantum computing strategy. We're not developing a quantum computer nor the hardware for it, but we're really focused in on algorithm development and where we can possibly see applications of a quantum computer for the U.S. Air Force. This breaks down our quantum program across the Air Force Research Laboratory. I'm in charge. My day job is being the Deputy Director at the Information Directorate in Rome, New York, but I'm also in charge of developing our strategic partnerships for quantum information science across the enterprise, across those four areas, as well as being a senior advisor to that team that is working on all these programs. I won't go into great detail, but you can see the two-letter acronyms are what we call our technology directorates in the different areas that they're working. So just for example, in New Mexico, down here, we have the Starfire Optical Range, which does ground to space communications, as well as our quantum sensor work, our quantum clock work. In Rome, New York, where I'm located, we are working on quantum networking as well as the quantum computing algorithms. Another key area to point out would be our Air Force Office of Scientific Research. Why that's of interest is that in addition to funding universities in the U.S., they also fund universities through our 5 international offices globally across the world. So we're really able to look at the different technologies, especially at the university level, fund them for their development, and then ultimately partner and bring those technologies to bear in our deeper based programs. You can see the international sites listed down here as well. All right, let's jump into quantum networking. So I think this slide does a great job. The acronym, I apologize up there, RATQ, that's just our internal branch or section name for where we're developing the technology. If we focus in on our open campus and our in-house laboratories, the first thing I want to point out is this is where we're talking about our different qubit technologies. So we're developing 3 types of qubit hardware at AFRL: superconductors, trapped ions, and integrated photonics. And of course, a key to that would be bringing the different frequencies of operation together through processes we call transduction. Very difficult process. We've been working on that for several years. The reason we're doing all 3 of those processes, all 3 of those qubits, are really those we see a need for those, for the need for a heterogeneous type of network where it's not going to be developed all with a single type of qubit. Similarly to quantum computers, where different modalities are being developed, not quite sure of the winner yet, we see the same kind of thing and the same strengths, and in some cases the same weaknesses being brought to bear there. We see these across different applied areas. So where we're moving towards, and this is where I'm going to spend the bulk of our time talking about, is how we go from really basic research being developed at our Open Innovation Campus, what we call Innovare Advancement Center, to our in-house laboratories, and then finally how we can go from lab to field. And this is very important to us because it's great to have these technologies being developed on optical tables, doing very confined, well-constructed lab experiments. But it really matters to get them out into the field and the engineering that you need to then do to that. And that's why we've really developed our test bed and had that emphasis the last several years. With that said, of course, we realize that we're going to keep having to do basic development over at our Open Innovation Campus, more applied development within our laboratories, but really bringing this all together and have this kind of circular loop development, if you will. All right, this gets into our actual network topology and the different places we're developing it, and I'll go into each of these. So our real vision is to develop 4 different what we call quantum local area networks, QLANs. 2 at our local campus, Griffiths, and the Rome Research Site, which is RRS, our offsite facility, Stockbridge. And then finally, which we have not implemented yet, would be our Newport QLAN. You can see the use cases discussed here: secure communications, distributed quantum computing, distributed quantum sensing, which I hope to hit upon in a little bit. And then really being a test bed for others to bring their qubit technologies, their network devices, their network appliances, if you will, and then bring them to our facility to be able to ring out and really test them as well. And I should say, when you talk about secure quantum communications, you can see it up there. What we're really interested in is entanglement distribution. So our position in the U.S., is particularly in the Department of Defense, is do not fund quantum key distribution until it is able to be proven out enough where it can be certifiable, and then for us to use it in our actual network. So we don't discourage the research, but it's not something we're doing internally. We're kind of taking a look forward as using these heterogeneous networks for entanglement distribution. So now let's drill down into each of those. So our first network that we set up was called at Griffiths. Griffiths is the site of our local county airport. It's located just really across the street from where our location is. You can see the runways there. Our Innovare is our Open Innovation Campus, and this is the fiber loop. So we initially set up 2 networks within our laboratories, 10 kilometers and 5 kilometers. We've then grown that to is to be able to take that out into a fiber loop that goes deeply buried, relatively deeply buried. Why I say deeply buried relative will come apparent when I talk about Stockbridge. We have a ring type topology where we have our different sources. And our goal here is to, as we set this up, as you might imagine, as we're developing these different qubits, is to make it agnostic to the qubit technology. So being able to bring in those different types of sources and put them into the network in terms of this actual type of test bed. Some of our resources and capabilities, as we go through this talk, it's going to become very apparent in terms of time tagging, multiple entanglement sources, single photon detectors, all those key elements that you would need, of course, in a quantum network. Next slide, if you recall, and I'll go through this within the next 10 minutes or so. We're going through our different networks that we have set up. This one is at our research site, a Rome Research Site, so just across the street, but inside our security perimeter. Only difference really here is we're connecting labs to a walk-up tower, so we have this aerial piece added in to our indoor lab spaces as well, which again allow us to switch out the different qubit technologies and look at different environmental conditions. Next slide. Now we talk about our Stockbridge site, and this is very unique, so I want to spend a few minutes on this. So we have pads placed throughout this 300-acre site, and you can see the yellow dots really illustrate the different pads. We call this our controllable contested environment. It's located about 30 kilometers away from our main Rome Research Site. And here, through these series of pads or shelters, what these really do is it allows us to create an RF spectral environment that we would see, in a typical type of conflict or war or whatever environment we might be in. Now we've taken that, we've modified that to set up some control nodes for our quantum network. You can see some of the areas here, nodes placed throughout the site, fibers connecting them, and really several pads, so labeled A, B, C, D, and E here, command center, walk-up tower, and this includes both free space and aerial nodes. So recall the Innavari site or the Griffith site, as it was labeled there, is a ring topology. Here we're doing more of a star type topology. Next. So this shows actually in one of those nodes. This is what one of those shelters looks like. We also have a large walk-up tower that gives us that aerial piece. And here's really the heart of the networking. You can see a few things here. You can see the single nanowire superconducting photon detector right there, the single photon detector. Polarization control equipment there, and then the rest of the control equipment for the node. So put in that shelter, really neat way to set things up. Next slide. Here's the control links for this. So again, really the ring topology at Griffiths, where we have the loopback with the fiber links set up by a single Ethernet switch there. Some of the control electronics, some of the pretty neat stuff. So time synchronization with White Rabbit, kind of bringing all those pieces together. Then as we move to Stockbridge, our star topology, a little more complicated because it's non-looped fiber. So we really have to bring in some more classical local area networking technologies to bring it together, as well as some very dedicated fibers to run that. But you do see some of the different pieces, including the pink button, the automated polarization control, which we're going to show some results from. Next slide. So this shows Griffiths, and I will say on all the results I'm showing here, there's an archive paper posted back in August from our team, Dr. Aaron Sheridan, primary author. It's a long paper, goes through a lot of detailed analysis, total of about 50 pages, goes through all of the results in detail. I'm kind of just hitting the high points here, given time limitation. But this goes back to Griffiths. I talked about we had the 5 kilometer and 10 kilometer buried fiber between parking lot and street. So we did a lot of characterization. And one of the things that we're really looking at, I talked about, our goal here is to get from the lab out into the field and see real world type conditions. So being outside, being buried, having wind fluctuations, having temperature fluctuations. See the temperature is captured here over a period of 60 plus hours. And what we're really looking at here is the state of polarization. And this is with the polarization control turned on. Otherwise, we don't have it here, but it was really just dropped down and we had all sorts of real noise with the state of polarization. Turned it on, our goal was to trigger once it got to 98.5% fidelity, to bring it back up to the goal of 99.5% of polarization fidelity. You can see when it would drop off, it'd kick back on and be very stable. So this was a great improvement for us and really one of the high points of the results. Measured as a function of power, fidelity, the azimuth angle, as well as temperature as well, is laid out here. And again, recent results taken not too long ago on the 5 kilometer network. Next. Now moving on to Stockbridge. Similarly here, you can see a lot of the environmental perturbations and characterizations that we carried here in terms of wind speed, temperature, state of polarization, of course, which is most interesting as a matter of time. So I talked about earlier the Griffiths network, the fluctuations, even worse at Stockbridge down here, might be a little hard to see, but really dropped off after initially clicking on the network. But we bring on the APC, which is from QNECT, their automated polarization controller. Really done a great job. We've worked with QNECT for quite a while. So to actually put it into a free space environment was really neat for us, and as the first demonstration of this type of stabilization with that type of system. So a real landmark for us. You can see the really nice clearing polarization there as well. And if you want to get into some of the details of these measurements, I refer you to the archive paper as well. Next, please. Here's our vision for where we're going. So talked about QLAN setup, link characterization. Our plan, as I mentioned earlier, if you recall, our other offsite facility is Newport, which sits similarly about 30 kilometers, but due east of our main site in Rome. So we'll be setting up a similar network there. Then as we link those together, forming a metropolitan-based type of network. Expanding into a sensor type of network, as well as free space components. So one of the things we're working on is how to put some of our qubit technologies on drones. We've demonstrated it with integrated photonics. We're now going and really challenging ourselves with ion traps. So partnering with Inflection, how to develop a very compact ion trap that can be put on small drones, very much of interest to us. You can see the mobile nodes. And then finally, the sensors. Rydberg sensors are of interest to us. So we're starting a new program this coming year where we'll be looking at taking the line technology and integrating Rydberg sensors into it. And the first step is to put it out at Stockbridge into that as well. And of course, bringing everything together with the different qubit technologies demonstratable in the field is our long-term goal, 10 plus years out. Next slide. And this goes through a lot of that. So really bringing together the photonics, the superconductors, and the ions, and developing the transduction between that. Fieldability and ruggedization, you can see as I've stepped through this, both parts of the presentation have been key to that. So something we're really driving towards. And then ultimately, when you think about it, we're demonstrating with fiber, but being the Air Force, being the Space Force, free space is going to be much more of interest to us. But certainly there's always going to be fiber-based components that are needed. Next. All right, next slide. So I'm just going to, I know, very short on time, but I always get asked, the relationship between our computing program and our networking program. I had mentioned early on when I talked about our strategy at Air Force Research Lab, we don't develop hardware for computing, but we develop it for networking. But what we are doing is we are doing hardware viability evaluation. And by that, I mean, we're one of the 6 test and evaluation teams for the DARPA Quantum Benchmarking Initiative program. So we have a dedicated team working with DARPA, looking at the different performers under QBI and really looking at how those companies can possibly get to quantum advantage and will their system be tolerable for a fault tolerant system. What we are working on in-house is algorithm development and state-of-the-art with today's evaluation, partnered with certain providers out there. Specifically, we worked with IBM for about 6 years, as well as IonQ for the last few years, on looking at some of the algorithms and potential use case applications for the Air Force. You heard in the morning sessions today, as hardware continues to scale, but we really still need those applications where it'll be viable and it makes sense for the Air Force to look at use of quantum computers. Next. So finally here, this I won't go through it all, but as we bring our team up to speed, as we bring other users across the lab, really developing that workforce. So having a full library of quantum algorithms, ones that we've run as well. I think everyone will be probably familiar with those. And then really taking those, running them on the NISC hardware that's out there so we can really get an understanding at the very basic qubit level. I mentioned the 2 commercial providers, always interested in looking at other providers, but really we're limited not so much by other factors, but really limited by the manpower and our available personnel to be able to broaden too widely. Next. And so finally, I'll wrap up. I showed a very large strategic view of the Air Force Research Laboratory's Quantum Information Science program. We can't go at it alone. So we have many partners there, spanning from our government partners, academia, industry, international partners, very key to us as well. If you don't see your logo up there, please, and you're interested in working with us where it fits in, I can't guarantee that we can work with everyone as we're limited as to what we can do in terms of our manpower. But certainly if you see a strong alignment with what I presented today, please feel free to reach out to me and discuss further. And with that, we made it to the end twice. Next slide. Yep.
Thank you very much. Do we have any questions from the audience?
Sure.
I'm interested in the quantum computing collaboration with the University of Wright State next to the Wright-Patterson. What is actually the project there, and Do they
yeah,
engaged with you?
Wright State University. Yeah, we've worked so kind of a program with Wright State Air Force Institute of Technology. We've done classes, developing a class with Air Force Institute of Technology, then specifically with Wright State, partnering with them on looking at algorithm development that we could, run on the commercial-based quantum computers, as well as some student training with that. Yep, great team there.
Thank you very much. Basically, we're using mostly the buried fiber for more than 2 kilometers. Is it any restriction that you are not going to use the free space optical communication? Is it just because of that they are not reliable for the moment, or is there any other restriction that, I mean, if the technology goes there that you can go up to 3 kilometer, 5 kilometer, 10 kilometer with high precision, is there any restriction that you would say no, we're not going for free space communication?
No, you're spot on. Great question. We're actually looking, the other way. Sooner we can probably get to more free space will be of interest. Hopefully at some point I'll be able to show some of our satellite work as well, some of our ground to space work that's run out of New Mexico with one of the international partners. Not ready to show any of that yet, but that's certainly of interest. And we'll definitely be expanding the free space quantum links. We're taking advantage of some earlier work we've done in free space optical communication. So the pointing and tracking systems that have been developed under that we'll be using. And and one of the walk-up towers I didn't show, but there's actually a pointing and tracking element there as well that we're using, so highlighting that. But great question.
Okay, let's thank the speaker once again.
Thank you for your patience.